Hello, welcome to Stat 310, Lecture 14. So we're going to continue our discussion on hypothesis testing, which is Chapter 9. We're going to quickly, to begin with, just go over some of the basic notation. A lot of new concepts and notations were introduced in the previous lecture. I'm just going to remind everyone of those, and they'll all hopefully become more and more familiar as we start to use them more. And then we're going to kind of move on to a particular kind of testing framework that is very widely used, which is related to this concept of likelihood, which we learnt about in Chapter 8 when we're talking about maximum likelihood. So we're again going to talk about likelihood, but in the context of testing. So in particular, we're going to introduce the likelihood ratio statistic, which is going to form the basis of a likelihood ratio test. And that's going to lead to, I guess, one of the crucial results of the Neyman-Pearson lemma, and we'll talk about what that actually is as we go through the lecture. So I just wanted to remind everyone of some of the key components and the concepts around hypothesis testing and the framework that we'll be using and developing in this course. So to begin with, the first thing you need is a hypothesis. Like, that's kind of saying that you're trying to test whether a hypothesis is true or not. So there's always two hypotheses in these contexts. There's a null hypothesis and alternative, and these typically surround a particular population parameter theta. So whether that be the probability someone votes Republican, the probability that the Green Bay Packers win a game or make the playoffs, there's some underlying parameter theta, and then there's a null and alternative hypothesis associated with that. And I just wanted to remind people and also talk about some of the different kinds of hypotheses that you can see. So in general, you assume that theta belongs to some set in R for H naught, and then theta belongs to a different set in R for H1. So there's no overlap between the two sets. That's what this statement up here is saying. And so to give you some examples of hypotheses, and we saw these in the previous lecture, but the main kinds of hypotheses that we're going to see in this course is there's sort of the simple hypotheses where theta equals theta 0, and that's a simple hypothesis because recall the definition that if you know the theta value, then you usually know the distribution of your x's, and that kind of tells. So that means you can do all the calculations surrounding the distribution of your x's. And then there's a bunch of composite hypotheses that come up. So for example, you'd have theta bigger than theta 0 or theta less than theta 0 are a couple of examples. And then you can also have what's known as a two-sided composite hypothesis, which is that theta is not equal to theta 0. So your null might be that theta is 0.5, and then your alternative may be that theta is not 0.5. It might be smaller than or bigger than. These three are composite hypotheses because you have different theta values, you typically don't know the distribution. And then for theta bigger than theta 0 and theta less than theta 0, these are one-sided hypotheses because, clearly like the alternative only sits, or that hypothesis only goes kind of in one direction. And it's two-sided because it in some sense has two pieces, one bigger than theta 0 and one less than theta 0. And one thing to just point out that in general, the null will often be a simple hypothesis, like we saw in the previous lecture, it was theta equals 0.5. While the alternative may be simple or composite. And we're going to see different examples of that. Today we'll focus mainly on the case where the alternative is a simple hypothesis, but we'll see that in general, in reality, the alternative is usually composite, and so we'll go into that case a lot more in the next few lectures. The second key component is the test statistic. So this is a function of your data. So we use this notation T of x1 through to xn. So we saw an example of a test statistic in the previous lecture, which was the x bar or the sample mean, and that's kind of a statistic we've seen a lot, and it can certainly be a test statistic too. We're going to see another kind of statistic here, which is the likelihood ratio, and so that's that's going to be kind of another pretty useful statistic. And we can often find the asymptotic distribution, like the asymptotic distribution or approximate distribution for sorry, let me write that out. For t of x1 through to xn, and then I should sort of add this under h0 or h1. So typically, like, the h0 or h1 kind of tells you what the theta value is, and then and then using that you can determine what the distribution is for the null for the test statistic. And this is a bit of a shift from what we've seen in previous lectures, where the distribution really depends on which hypothesis you're in or what your value of theta is. So the different hypotheses essentially break up the different possible values that theta can take, and that'll give you a different test statistic. And that's kind of a new concept in chapter 9 that we haven't really seen so far. The other thing that's kind of important in determining the overall test is a significance level alpha, and that will lead to kind of the acceptance and rejection regions. So your acceptance region, it has to be dependent on your data, because it has to be a decision based on your data or your test statistics. So if your t lies in some set A, then that's the acceptance region, and that's a subset of R. The rejection region is the composite of that, so that's like the opposite, like all the points that are not in A. And we're going to reject H naught if the test statistic lies in A complement, or otherwise we'd accept H naught. And just remember again that accepting doesn't really mean that you're saying H naught is true. It's just saying that you don't have enough evidence to reject the null hypothesis. And that was very clearly evident in the example we saw in the previous lecture, where even though the proportion of people voting Republicans was 0.55 in a sample of 100, we still accepted the null hypothesis, not because we believed it to be true. We just didn't have enough evidence to reject the null and reach that conclusion that the Republicans that we believe that the Republicans are going to win based on the sample we observe. And so one typical example that we saw in the previous lecture and is in general going to be true is that the test statistic is going to be smaller than or bigger than some threshold C, and that can be either acceptance or rejection. I've just used acceptance here as a convention, but it could be either one. And then the rejection would be the opposite. And then you to determine that critical threshold C, which in turn determines the whole acceptance and rejection regions, you use the size alpha. So the alpha, which is the size or significance level, is something you predefine. So it's not, it's not something that you calculate. It's something you typically predefine, and we predefine it as 0.05 in the previous lecture. And so we found that when we set it to 0.05, that gives you a value of C. So the way what we typically do to determine the acceptance or rejection regions was to find the probability that your T is bigger than C, given your theta was theta 0, which was the null. Like, this is kind of the notion that H naught is true, and you're looking at the probability that T is bigger than C. And then the final concept that we talked about in the last 10 minutes of the previous lecture was this notion of the power of a test. And so we use this notion beta to denote the type 2 error. So the power, we want that to be high. More powerful is better. And so 1 minus beta is the probability that you reject H naught given that H1 is true. So if H1 is true, you'd ideally want to reject H naught. So you want that to be a big number. And so as we saw in the previous lecture, if H1 is simple, so for example, if H1 is a single point, theta equals theta 1, power can be calculated explicitly because you can determine this probability under H1. But otherwise, you can't calculate an explicit value of power, but you can get a power curve. So for every different value of theta that lies in the H1, you can get a different value of power, and then it's going to give you essentially a power curve to say how powerful your test is. And so what's going to motivate our discussion on likelihood ratios, and in particular the likelihood ratio test, is we're talking about this notion of best or optimality, which we talked about in the context of estimation, where we sort of discovered that maximum likelihood was optimal from the perspective of being kind of the best asymptotically unbiased estimator. And so that's going to motivate this this notion of likelihood ratio as well, is we're asking the question, is there a best or optimal test that we can come up with? And what does best or optimal mean? And so what this means is, if we fix alpha, what is the most powerful test? Most powerful test. And so remember that alpha is something that you fix, and then power, in some sense, once you have your test, your acceptance and rejection regions for your test statistic, you can calculate power or get a power curve. And so the question is what's the most powerful test if you fix alpha? We measured the notion of optimality for estimation as minimizing variance. For testing, what we're going to use for optimality is we want tests that are the most powerful if you fix an alpha. So if we fix a particular alpha value, the size or significance level of your test, is there a most powerful test? So for example, we came up with this test that, if x1 is, Bernoulli, so this was the voting example. If x1 through to xn was Bernoulli theta independent, we had this test that, if h0 was, theta equals theta 0 and h1 was theta bigger than theta 0. And then, the test that we came up with was the test statistic was x bar. And then, we were, for fixed alpha, we had this test that, so if x bar was bigger than some threshold, you'd reject h0. And that's again because we have theta bigger than theta 0, so this is one-sided. Then you'd reject h0, and then x bar less than or equal to 0, then you accept h0. Okay, and use C to find alpha use alpha to find the critical threshold C. The question that we're is this the best test? Is this the most powerful test? Alpha, or can we do better? Okay, and so this leads to, and this is we're going to get an answer to this question by the end of today's lecture, and we're going to build up to that by introducing this notion of likelihood ratio. And this is very connected to what we learned in chapter 8 on likelihood. So we're going to construct tests based on a likelihood ratio statistic. So So for today, we're going to assume that both H0 and H1 are simple. So theta equals theta 1. And the reason we're going to assume that is because that allows us to calculate the distribution of our test statistic under these two different models and under these two different hypotheses. And so We're going to extend this like in the next lectures and beyond, because if we stick to simple hypotheses, these are not very useful in practice, as we saw in the voting example. To lay the foundation, it's going to be easier to look at the setting where things are simple. And as we'll see, it's pretty easy to extend this to composite hypotheses, and we're going to do that from lecture 15 onwards. So I just wanted to remind people of this concept of likelihood, which we saw in chapter 8, which was, you had L of theta x1, x2 up to xn. So this was kind of this we multiply the distributions because we have independence. The joint PDF or PMF is just the product of the different PDFs or PMFs. Okay, and so this is the likelihood for fixed theta. And remember that the goal of maximum likelihood was to find a theta that maximized this likelihood. And we're going to see that that's going to be a very useful tool in this chapter as well. But what we're going to do here is say, from a hypothesis testing point of view, under these different hypotheses, you can actually calculate the ratio, the actual likelihood given your data, and then you want to use that to come up with a test. So under H0, which is theta, in this case, because we're dealing with the simple hypotheses, L of theta 0. This is like a, the likelihood under H0. Okay, and so this is, and this is actually a statistic, because since theta 0 is known, so even though you don't know theta, you know theta 0. So because of that, this is a statistic. And then under H1, our alternative hypothesis, which is now simple, which kind of makes our life simple in this case too. This is the likelihood under H1. And then this is also a statistic, since theta 1 is known. Okay, and so then this leads to the likelihood ratio statistic. Which is, I'm going to use this so this likelihood ratio statistic, which is a function of theta 0 and theta 1. And that's going to be just the ratio under the null and the alternative. Okay, so I'm going to talk about how this leads to testing shortly, but I just wanted to do some calculations of some examples of likelihood ratios. And again, this is very connected to the notion of likelihood that we've seen before. So sorry, let me write this properly. Because you're taking the product, you only need to look at them one at a time. Okay, so this is the case where we have x1 through to xn is normal mu sigma squared. We're going to assume sigma squared is fixed and known. So it might be 1 or 2 or something that's fixed and known. And so we have our h naught is mu equals mu 0, and h1 is mu equals mu 1, where they're not equal. Let's find the likelihood ratio of so remember that f of xi mu, we're treating the sigma as a constant, is just 1 over square root 2 pi Okay, so this is the PDF, sorry, of the normal distribution. And so if we look at the likelihood ratio, so this is going to be so now we plug in our mu1 and our mu0s here. Okay, and so just like in the case of maximum likelihood, a lot of nice things happen here that make our calculation kind of look a lot nicer and a lot simpler. So you're going to get cancellations here because they're ratios, and the product of exponentials is the exponential of the sum, and the exponential of the quotient of exponentials is the difference of that. So we can rewrite this now as okay. So this is what we get, and if we expand this out, probably better to put the bracket here just to avoid any confusion. You can see that the xi squared, so I'll write out the full expression. Okay, so all I've done is just expanded everything out, and we get a very convenient cancellation here. And you can re-express this now as okay, so and like when you so if we let that statistic x bar equals 1 over n, summation I equals 1 to xi, this very nicely can be expressed in terms of the the sample mean. So I'm going to remove this negative sign and just, we're going to get, and this is going to be okay, so I'll simplify it one more step here. So that gives us so note that depends on only through x bar. And this is very kind of convenient because what we're saying is that the likelihood ratio statistic, even though it depends on all of the data, we can express it entirely in terms of just x bar. Okay, and I mean the exact expression here is not super important. The one thing to note here is that as x bar times mu0 minus mu1 gets bigger, the likelihood ratio gets bigger. And this kind of makes sense if we think about it, because remember that the likelihood ratio is really looking at the question of how likely you are to observe the data given a particular hypothesis. So note that if mu0 is bigger than mu1, as x bar gets bigger, likelihood ratio gets bigger. And if mu1 is less than, if mu0 is less than mu1, as x bar gets smaller, likelihood ratio gets bigger. Okay, and this kind of makes sense because, if your mu0 is bigger than mu1, you would kind of expect that the likelihood of observing that is that the likelihood of observing that is going to be as x bar gets bigger, you kind of have more evidence to suggest that the mu is bigger, which is what this likelihood ratio is trying to achieve. So the idea here is that develop a test such that if likelihood ratio is bigger than some c, or bigger than or equal to some c, this will be like an acceptance region, except h0. And if the likelihood ratio is smaller than some c, we'll reject h0. And so this is the basic idea behind the likelihood ratio test, and we're going to kind of see that shortly. We're going to do one more example there. This relates to our earlier example. So if we have x1 through to xn is Bernoulli theta, and then our h0 is theta equals theta 0, and our h1, our alternative, is theta equals theta 1. Let's look at the next thing we need to calculate the likelihood ratio is this f. And remember that we have this very convenient trick that we can express this as theta to the xi times 1 minus theta to the 1 minus xi. Since xi is Bernoulli in 0, 1, this is how we can kind of express the PMF for this. So we use this for the maximum likelihood, and we can again use this here to calculate likelihood ratio. Okay, and so if we look at the likelihood ratio of theta 0, theta 1, okay, and once again, like we get a lot of very convenient things happening here. We can rewrite this as so all I've done is used properties of okay, and so if we again let x bar as you can express this likelihood ratio that's theta 0 over theta 1 to the n x bar, and then n times 1 minus x bar. And so you can kind of rewrite this whole thing as so you can kind of express this whole thing as okay, so just recalculating things, we get this this simple expression in terms of theta 0 and theta 1. And so note in terms of x bar again. And the other thing to note here is that if theta 0 is bigger than theta 1, as x bar increases, likelihood ratio increases. And, if theta 0 is less than theta 1, as x bar increases, likelihood ratio decreases. Okay, and so these are sort of very useful, concepts, and this is going to lead to, we're going to talk about the likelihood ratio test. So the likelihood ratio test, so we have our test statistic is the likelihood ratio. Once again, remember that we're only talking about the cases where the null and alternative are simple for now. We'll move on to the more complicated cases where things are composite a little bit later. So this is our test statistic. And then what we need from there is that, like, note that okay, and so note that as LR, I guess I should say, okay, so let me just kind of explain this logic a little bit here. So remember that the likelihood ratio is the product of these, is the ratio of these likelihoods of the likelihood under theta 0 and the likelihood under theta 1. So clearly, because the numerator there is the likelihood under theta 0 and the denominator is the likelihood under theta 1, you kind of expect that if the likelihood ratio is bigger, that suggests that you want to accept H0, and then the likelihood rate, if the likelihood ratio decreases, then you're more likely to want to reject H0. And then, so this leads to the likelihood ratio test. Which asserts that, so I guess like the test is determined by the acceptance and rejection regions. So the acceptance region then would be that the likelihood ratio, that should be bigger than or equal to C. And the rejection region would assert that the likelihood ratio is less than C. Okay, and so how do we determine C? And so this is a question that if I ask you this, after thinking about it, you should be able to come up with a reasonable answer. And so the answer is that use significance level alpha. So remember that alpha equals the probability that you reject H naught, given that H naught is true. So in this case, that is simply just the probability that T of x1 through to xn is bigger than or equal to C, or sorry, it's the other way. Is less than C, given that theta equals theta 0. So we can think of that as the probability of the likelihood ratio of theta 0. And that should be equal to alpha. And so note that so C, which is the threshold, depends on alpha. So let's return to the example of And so remember that the likelihood ratio there, so here sigma squared is fixed and constant. And then we had okay, I believe that's correct, but you can check that. And so one thing to note is that so this quantity being bigger than or equal to C, that's equivalent to x bar times mu 0 minus mu 1, being bigger than or equal to some C tilde. This is a different C, obviously, but you know, those two are equivalent. And so to find C tilde, we note that under H naught, which is mu equals mu naught, we have that xi is going to be distributed normal mu naught sigma squared. And so the x bar is, now we can, in this case, we can calculate the statistic exactly. That's going to be distributed normal with mean mu naught and variance sigma squared over n. Therefore, we note that root n, so hopefully these are calculations you're comfortable with at this point. It's a normal 0, 1. And so so alpha equals the probability that you reject H naught given H naught is true, or I'll say given that mu equals mu 0, which is equivalent to the probability that x bar times mu 0 minus mu 1 is less than C tilde, given that mu equals mu 0. And since we know that square root of n x bar minus mu 0 over sigma is normal 0, 1, we can use the standard normal tables to actually calculate this threshold C0. So I'm also, just for simplicity, just going to assume that mu 0 is bigger than mu 1. If mu 0 is less than mu 1, you just have to worry about like when mu 0 minus mu 1 would be less than 0, so you'd have to flip the sign. So the sign gets flipped, which kind of flips the test, which is what you'd expect it to. So I'm just, for simplicity, keeping mu 0 bigger than mu 1. And so this is just the probability of the z being less than square root of n, z tilde. Okay, and we want this to be equal to alpha. This is the size. So then we can kind of think of using the normal table. This is the area alpha. And so the z alpha is going to be a negative value here. So we're going to say that that should be equal to z alpha. Therefore, this critical threshold here should be equal to plus mu 0. So and so the idea would be that reject reject h naught if x bar times mu 0 minus mu 1 is smaller than and so equivalently that's just the same as x bar being less than okay. Sorry, I've done something wrong here. Yeah, so I think that this final answer is correct. Right. Yeah. So I think So I believe this final answer should be correct. And note that you can see that this is like the z value for confidence intervals. And we're later going to see a connection between the confidence intervals and the and these hypothesis tests. So this kind of the calculations are actually very similar to what you've seen before, but yeah, we're doing it in this testing framework. And then for the case the likelihood ratio depends only on theta again. Oh, sorry, only on x bar, theta 0 and theta 1 again. Therefore, x bar bigger than c, x bar less than or equal to c is equivalent, or we'll say c tilde, so it's not the same. It's equivalent to the likelihood ratio test. And then as an exercise, I'm going to say, like, use the CLT, the central limit theorem, to find values of c tilde in terms of n, theta 0, and theta 1. Okay, and so now let's return to the question of, so what's the most powerful test for a fixed alpha? And this leads to the Neyman-Pearson lemma. This is in 9.2 of the textbook, and this asserts that for a fixed significance level alpha, if H0 and H1 are simple hypotheses, no test has more power than the likelihood Okay, and so this is pretty useful and pretty powerful because it's basically saying that the likelihood ratio test gives us a general procedure to find a test for, for any kind of distributional scenario we can think of. And on top of that, we're actually saying that that likelihood ratio test is kind of the most powerful test you can come up with for a fixed alpha. So remember, just to kind of spell things out a little bit more, that the likelihood ratio test, just to kind of step the procedure out, there's the first element is the statistic, which is just that the likelihood ratio of theta 0, theta 1, x1, okay, so this is the likelihood ratio test statistic, and the actual test. Acceptance region is just the likelihood ratio that should be bigger than or equal to C, because we're going to more likely to favor, and so the acceptance region just means you accept H naught. So just to spell this out, our H naught is theta equals theta 0, and our H1 is theta equals theta 1. And the rejection region is the likelihood ratio Xn is less than C. And then note that to find C, you fix an alpha, fix an alpha and use exact or approximate distribution of the likelihood ratio, or equivalent. And why I'm saying or equivalent is, remember that for the normal, the likelihood ratio was that exponential, but because we could write it out in terms of the sample mean, we could use the properties of the distribution of the sample mean. Later on, we're going to see that sometimes you can actually find the distribution of the likelihood ratio test statistic directly. But in this case, it's easier to use the sample mean. So to find C, you fix alpha and use the exact or approximate distribution of the likelihood ratio, or the equivalent, because you know that all you really need to find is that C. And if you can find that C in terms of a different statistic that's related to likelihood ratio, that's all you need. And then, so the Neyman-Pearson lemma asserts that no test is more powerful than this. Okay, and so that's kind of a pretty cool and useful thing because it gives us a general way to find tests that we know can't be beaten. And so then, you know, this again emphasizes the importance of likelihood theory, because remember that we developed this general maximum likelihood procedure and showed that in some sense it's optimal for estimation. And now we have this testing procedure, which again is related to likelihood ratios and you know, in particular the maximum in terms of likelihood and likelihood ratios. And it turns out that this is the best you can do as well. And so just as a preview of what we're going to see next, so, you know, can we form or make similar conclusions if H0 and or H1 are composite? Because simple hypotheses in some sense are the easy case, but they don't kind of cover a lot of important real-world applications. So for example, you know, will the Republicans win the election? Like the alternative hypothesis was certainly composite there, and this likelihood ratio theory doesn't really cover that case yet. But we'll see that we can extend this to look at composite hypotheses. And so just as the last thing I'll say in the last 2 or 3 minutes, so how do we extend likelihood ratio statistic to composite case? So say we have H0, theta is in S0, and H1 is that theta is in S1, and we know that S0 intersect S1 equals the empty set. And so then we can say that the likelihood ratio, which is now going to be a function of the sets S0, S1, and then X1 up to Xn, we're going to do this notion of maximizing. So for convenience, what I'm actually going to do on the denominator is take the union. I'll talk about why I do that in the next lecture. And then, so we need to calculate maximums over theta. And so how do we do that? And so hopefully this connects back to what we've already studied. We're going to use maximum likelihood to do these calculations. Okay, and so this is going to be something that we'll talk about in the next lecture. But this is going to be like, so hopefully this brings together what we learned in the previous chapter on chapter 8, where we're looking at maximum likelihood and what we do in this scenario of hypothesis testing. Okay, thanks. That's it for this lecture.